that we were practicing on Thursday. I know it's been a few days, but take a minute and look over it and see if you have any questions you would like me to go over. Go ahead, Sienna. 4? So we're asked to determine the value of A in this expression. And it seems weird. It seems like a very weird question. But let me rewrite it. We have A multiplied by cos squared of pi over 8 minus A multiplied by sine squared of pi over 8. This is equal to 4 root 2. Now, this is a numerical response question, and you're asked for the value of A to the nearest tenth, which means nobody really cares how you solve this. So I want you to note, everybody, that in this equation, everything that I'm highlighting is just a number. Don't get lost in, there being a pi. Sine squared of pi over 8 and cos squared of pi over 8 and 4 root 2 are all numbers. In fact, what this equation is a linear equation. It would be no different in principle to solving this equation. I mean, it looks different, and obviously it's different because there's trigonometry, but this A cos squared pi over 8 is just cos squared pi over 8 times A. It's like 6A. And when you solve this kind of equation that I've got as an analogy to the original question, you just look at it and you go, well, I have to subtract 6 minus 2 and get 4A. It's not obvious what you have to do here. But what you can do instead of subtracting 6 minus 2 or 6A minus 2A is you could factor out the A. And we went from having A in 2 places to having only A in 1, so we can then divide 105 by 4. You get my drift there? Okay. Well, that's what we can do here. We can factor out the A and have cos squared of pi over 8 minus sine squared of pi over 8. And now I'm going to go back to the idea of a numerical response question. You could actually calculate this. You could take sine of pi over 8, quantity squared, minus cos of pi over 8, quantity squared, and then take 4 root 2 divided by it. However, we can do that if you want, but however, this could be a little too mark written response question. Right? So you would need to be able to show your work. And what we want to do is look at this and see that it is something of the form cos squared theta minus sine squared theta, which is cos of 2 theta. And I know on your formula sheet it uses alpha, but cos squared minus sine squared is the same as cosine of twice that angle. And that means here, Sienna, that we can write this in brackets as cosine of 2 times pi over 8. And 2 times pi over 8 is pi over 4. So we have cosine of pi over 4. And pi over 4 is an angle whose coordinates on the unit circle we are intimately familiar with. We should know that at pi over 4, the x-coordinate is root 2 over 2, and the y-coordinate is also root 2 over 2. But I'm focusing on the x-coordinate because it's cosine, and cosine is the x-coordinate. So this cos of pi over 4 becomes root 2 over 2. And now we have to solve this for A. The root 2's cancel. What's happening there is if I divide both sides by root 2, they go away, leaving the numbers 1 in their place. And I'm left with A over 2 equals 4, so when I cross multiply, I get A equals 8. Is that okay? All right. And again, you know, at this stage here, this isn't, in my mind, a really good question in Math 30 because you could, just getting to this step, find the answer on your calculator. But sometimes these slip through. So once again, you could take 4 root 2. I'm going to do this all in one shot. 4 root 2 and divide by the cos squared pi over 8 minus sine squared pi over 8, which would be cos pi over 8, close brackets, squared. I know, again, it might look to you, everybody, that I'm only squaring the pi over 8, but that's the way the calculator works. The squared goes outside of the pi over 8, but it's actually going to be squaring the cosine. Minus sine of pi over 8, quantity squared. Close brackets on that. Check to make sure I'm in radians. And you get 8. But, you know, again, anything that's numerical response could be written response. Other questions? Go ahead, Farhan.
On page 28, could we do 1C?
1C? Certainly. Is it this one? 2 sine squared 2x minus 2 cos squared 2x? Okay. It's a good question because it's very closely tied to what we were just talking about. I want to talk about the double angle identity, and I'm going to use the cosine double angle identity here because this is going to be connected to cosine. The cosine double angle identity, one of them anyway, is cos squared of alpha minus sine squared of alpha is equal to cosine of 2 alpha. And I had this conversation with somebody near the end of class. I don't remember who it was on Thursday. But, you know, what's important here is that the two trigonometric squares that are being subtracted have an argument that's an angle that's half of the angle on the single cosine. So in reality, I could write cosine of theta equals cos squared equals cosine squared of 1/2 theta minus sine squared of 1/2 theta. It doesn't matter what the angle is. What matters is that the single trigonometric ratio has an angle in it that is twice the trigonometric ratio on each of the square trigonometric ratios. So I could write as well cosine squared of 2x minus sine squared of 2x equals cosine of 4x. And that's kind of where I'm going here, because when you look at the original question, 1C, you see an argument that's 2x. Now, we have another thing to contend with, and that's that, well, we have a couple of things to contend with. There's this 2 here, but I can very easily factor the 2 out. So, 2 is going to be part of our answer, that 2 that we factored out. But I want to focus our attention on what this is. Now, I'm just going to ask, how many of you see that that thing that I've underlined is negative cos of 4x? Looking at this. I mean, you may not. The tricky thing is you have to understand, first of all, that cos squared of 2x minus sine squared of 2x is cosine of 4x. Okay. How many of you don't see that immediately? Because what you could do is you could factor out, instead of a 2, you could factor out a negative 2, couldn't you? And then what the sine squared of 2x becomes is minus sine squared of 2x. And what the negative cos squared of 2x becomes is positive cos squared of 2x. And then, I'll just squeeze that in. That's a little sloppy, but you get the idea. Then you can see here that this is the cosine of 4x. Does that make sense, Farhan? Okay. So what we end up with is negative 2 cosine 4x. Any other questions? Go ahead, Liam. 5a. And is that in the extra stuff? Textbook? You mean the questions that are in the handout? You're talking about this? Okay. So, just as an analogy, if you see, and this has nothing to do directly with this question. Well, it kind of does, but that's not my point right now. If you see sine of x over cosine of x, you should be seeing tangent of x, right? It's that kind of, it's that simple kind of thing. It's like seeing the word bonjour and understanding that it means hello. There's an idea behind it. Similarly, when you see sine of 2 theta, you should see that, or very soon you should see that. The double angle identity for sine is sine of 2 theta equals 2 sine theta cosine theta, and this is over 2 cosine theta, so the cosine thetas cancel and the sine and the 2's cancel. I want to make a more general point here. The reason why I'm able to cancel the cosine with the cosine is because cosine is a factor of the top and a factor of the bottom. I know it's a factor because it's being multiplied by other things. But if this were ever the case, on the bottom you had 2 minus cosine theta, you would not be allowed to do that. Does that make sense? Okay. Other questions? Yeah. Number 10. Okay. This one. So this is a perfect illustration of you have only one choice. And it's to start walking. And in this case, what you're going to do is you're going to be looking at the sum and difference identities for cosine. So this isn't going to have, I don't think, anything directly to do with the double angle identities. But when you look at your formula sheet, cosine of a plus b is equal to cosine a cosine b minus sine a sine b. Can you help me out after a long weekend of not teaching? Is that the right identity? It is, okay. And then, just to be a little sloppy here because we're in learning mode, if this were minus, this would be plus. Right? So now we can apply these identities to these two terms. Cosine of pi plus x will be cosine pi cosine x minus sine pi sine x. And we are going to add, we don't really need a set of brackets here, but indulge me and I'll talk about that in a second. Cosine pi cosine x plus sine pi sine x. We don't need this set of brackets, but if this plus right here that I'm pointing at were minus, we would need them. So they don't hurt on paper, but they're not necessary in this case. What we should now be able to do, is that okay, Grant? What we should now be able to do is figure out by hook or by crook, which means I don't care how, what the value of cosine pi and sine pi are equal to. Now I'm a unit circle kind of guy, so I just imagine rotating the terminal arm around to the location where the rotation angle is pi, which is on the negative x-axis. The coordinates of that point, when I rotate over here on the unit circle, are -1, 0. On the unit circle, cosine is the x coordinate, so cosine is -1. Cosine of pi is -1. Sine is 0 because it's the y coordinate. Plus, I'm going to peel off the brackets. Cosine pi is -1. Well, it's almost the exact same thing, except there's going to be a minus here. Minus sine of pi is 0. Are we okay with that, Grant? Okay. 0, of course, times anything, and I'm not sure why I put 0 there. There should be an x. Not that it matters. 0 times sine of x is gone. It's not that it cancels, it's 0. And the same with the 0 times sine over x. Sine of x here is 0. So what I'm left with is -1 cos of x, which is negative cos of x, minus another cos of x, which is -2 cosine of x. Is that okay? All right. Any other questions? All right. So we're going to spend some time working on proofs now. Trigonometric proofs. I think this is page 15 of your unit handout. When we first started learning about identities, and I hit you with those like 8 identities, those, or however many there were, reciprocal, quotient, Pythagorean, we learned about it on one day, and then the very next day we practiced, and that's what's going to happen now. And it's going to work out good because this lesson might be, well, it is going to be very intense for some of you, and it might go quite late into the period, but then tomorrow we have the seminar and our regular period. So the plan is to get through this lesson, maybe get started on some of the practice, but to do the practice tomorrow primarily. And work on some overnight too. You should be practicing continually. So we're going to be looking at proving trigonometric identities algebraically. And I also want to focus now again on non-permissible values. We talked about them before, but I would like to actually, we'll do this first. You have this pink sheet that I've given you, right? And on the pink sheet, it gives you a list of suggestions for working with identities. So I didn't print this out. I just didn't have time this morning. But this, I could print out a new one that says, when proving trigonometric identities, well, try replacing all ratios with sines and cosines. You already have that on your list, right? That's always a good idea. By the way, when you're proving an identity, you're working with identities. Remember to keep an eye out, keep your eyes peeled for things that are recognizable. Cos squared theta minus sine squared theta. Cos squared theta plus sine squared theta. 2 sine theta cos theta. Things that pop in your head as being memorable from identities. Factor if possible. If you have fractions being added or subtracted, bring them together with a common denominator. And of course, if things get too messy, go back to the beginning and start again. But there's something else, and I've mentioned this before, that is important for proving identities. Keep your eye on the side of the identity you're not working with. So remember, when proving an identity, we've done a couple of these, you work on the left side or the right side independent of the other side. You can't cross the equal sign, in other words. You can't start rearranging the equation. And what I'm saying is, if you're currently working on the left side, keep your eyes on the prize, which is what the right side is, because you want them to be equal to each other. So I just didn't have time to print this out, but this is the addition to that sheet now. Okay. Non-permissible values. So in terms of trigonometry, non-permissible values happen whenever you divide by 0 anywhere. Okay? That word anywhere is important. Okay, example 1. And you will see in this lesson that I give you a similar or directions to a similar example in your textbook. So if you're looking at what we end up doing with this one and you're having troubles, you can look on page 310 of your text and find the similar example. So what are the non-permissible values? Okay. Well, what we want to do is rewrite this, and this is not, we're not proving anything yet. We want to rewrite things so that they have primary trigonometric ratios. And on the other side, it's 1 minus cos squared, and I'm not going to write that down. So I told you, and non-permissible values are really tricky with trigonometry. I told you non-permissible values in trig happen when you're dividing by 0, which you're not allowed to do. Don't do that. You can't divide by 0. There's no division happening here. That's why I'm not even looking at it. I can put in any number for x I want and take the cosine of it and then square it. I'm not dividing by anything on that side. However, I am going to highlight things we are dividing by in the left side when I've written it in terms of sine and cosine. We are dividing by that. We're dividing by 1 over sine. Okay? We are dividing by sine, aren't we? We are dividing by 1 over sine because 1 over sine is under this line, which means we are dividing by 1 over sine. But within 1 over sine, we are dividing by sine. Right? We are dividing by cosine somewhere. And I know that you know, I hope, we can cancel these two cosines, but you have to find non-permissible values before you cancel. This goes back to rational expressions in Math 20. If I tell you to determine non-permissible values over this, of this, and you say, well, I can factor x squared minus 4 into x plus 2, x minus 2, and it's over x minus 2, so I can cancel that. So this thing is equal to x plus 2. There are no non-permissible values. Then we have an issue because there are non-permissible values. If you graph this, you will see there's a point of discontinuity in the graph. There's a break in the graph at x equals 2. X is not allowed to be 2. My point, and it's what I would like you to remember, is you determine non-permissible values before you simplify anything. Always in math. There's no exception to that. So these three things that I have highlighted are all things that we are dividing by, which means all of them are not allowed to be 0. And this is what you would be showing on a written response. So let's deal with these. Cos of x is not allowed to be 0. When you solve a not allowed to be equal to 0 statement, I don't want to really call it an equation, what you do is you say, where is cosine of x 0? Well, I'm a unit circle kind of guy, so cosine of x on the unit circle, or cosine of a rotation angle, is the x coordinate, which is 0 at the top and the bottom of the rotation. And that means that your non-permissible values, in terms of a statement for this, will be that x is not allowed to be pi over 2, which is the rotation angle of 90 degrees, which gives you a terminal point at the top of the unit circle where the x coordinate is 0, which means cosine is 0, and it's not allowed, plus multiples of pi because the top of the unit circle where cosine is 0, which is not allowed in this question, and the bottom of the unit circle where cosine is 0, which is not allowed in this question, are pi radians apart from each other. So as soon as I start adding or subtracting multiples of pi, I'm going to land in those two positions. This one, well, where is the sine of a rotation angle equal to 0 on the unit circle? It's equal to 0 at these two locations, at 0 and pi, and we can, you know, I guess if we think about this a little bit, we can just say n pi, can't we? Because if n is 0, that's 0. If n is 1, that's 1 pi, 2 pi, 3 pi, negative 2 pi, etc. We do, of course, have to add here that n is an element of the integer number set. You'll notice I kind of conveniently just ignored this middle one. And that's because the middle one never happens, ever. The only way, this is tricky, dealing with divisions and 0. The only way a fraction could be equal to 0 is if the top of the fraction was ever 0. 1 over some other number will never give you 0. It might give you undefined, but we've already taken care of that here. But it will never give you 0. Okay. I'll show you probably tomorrow different ways we can find non-permissible values, but I want to teach to a written response style question right now. That's what you would need to do. And you would probably also couple that, and I'm doing this as well for the video, you would couple that with the fact that you maybe have a diagram and at these points cosine of theta is equal to 0 because, nope, at those 2 points sine of theta is equal to 0 because the coordinates here have y values of 0. And you would probably say something on a written response that at these locations cosine of theta is equal to 0 because the x coordinates here are 0, and that's the cosine. So you would, you would explain it. All right, so now what we want to do is verify that this might be an identity either graphically or by choosing one value of x. Well, let's just do graphically. Let's enter into our graphing calculator. And I would like you to follow along with me. Let's enter 1 minus cosine of x quantity squared first. I want this one to be y1. And then we're going to enter tan x cos x over cosecant. Now, how do we enter cosecant of x? We have to enter 1 divided by sine x, because we don't have a cosecant key. But so I'm going to be dividing by 1 over sine. I'm dividing this that I've entered so far by a fraction, which means I'd better put that fraction in its own set of brackets. So the left side I've entered in for y2, tan x cos x over quantity 1 over sine x, and the right side I've entered for y1. It doesn't matter what mode you're in because we're going to go zoom trig right now. So zoom trig is zoom 7. 1 minus cos squared looks like that. Here comes tan x cos x over 1 over sine x, but it doesn't show anything, right? You understand that it doesn't show anything because it's graphing it right over top? Are you guys with me on this? Okay. So we could, to verify it, go to our tables and see that the y1 and y2 are always equal. You could go to y2 and change it to the little bouncy ball. by scrolling over to the left of the y and continuing to hit enter until you have that. And I'm doing this for a reason. Watch very carefully. Well, it's not doing it. That's interesting. I thought it would maybe stutter every time it hit one of those non-permissible values. I'm curious. I'm going to get rid of the 1 minus cos squared and graph it again. I don't know if you remember this or if your teacher mentioned it. Those breaks in the graph where we have non-permissible values are sometimes visible if you go zoom decimal. Do you remember that? We talked about it in Math 20 a little bit. So if we try zoom decimal, and I could explain why, but it's not really that important. Yeah, and it doesn't. But there are definitely non-permissible values there. If you were to go to your table and look at those particular locations, you would see there's an error. Anyway, we've verified it. That's the point. What we want to do now, and this is really the bulk of this lesson, is we want to prove this. How many of you see that these two things are equal? Like, I mean, you're almost like Neo in the Matrix, where you're seeing the matrix. But how many of you see how these things are going to turn equal to each other? It's not that tough, right? If you're starting to see these things, like you start to see tangent as sine over cos, and 1 minus cos squared is maybe sine squared. But here's how you do it on paper. I'm going to work on the left-hand side, and I'm going to rewrite this as sine of x over cos of x times cos of x over 1 over sine of x. But when you do a proof as a written response, you need to identify by name the identities you just used. What does that mean? It means because I used tangent equals sine over cos, I need to write quotient identity here. And because I used cosecant of x as 1 over sine, I need to write reciprocal identity here. I remember not having an argument with my high school math teacher, but saying, really? Mr. Von Holland, I actually have to write that? And Mr. Von Holland saying, yeah, that's the way we do it. And it's still the way we do it. What I have is a complex fraction. And the simplest way to simplify a complex fraction, and I'm going to duplicate it here. If you want to rewrite it, you can, but I don't really care what you have on your notes. I care, well, actually, that goes away, doesn't it? The coses cancel. But what I care is that you know, in order to really clean this up, you're going to have to multiply the top of this by sine of x and the bottom of it by sine of x. Because of this pest here. That over sine of x, that's a problem. I don't like mini denominators. What happens is I end up with a canceling of the sine of x, and I'm left with sine squared of x here. Sine of x times sine of x. I don't have to explain that. You don't have to explain algebra. And some of you were still doing that on written response. Quote, I multiplied the top and the bottom by sine of x because that's not an explanation of the math. Don't do that. By the way, the right-hand side was 1 minus cos squared of x. How many of you see these are equal? Everybody should, but we're not done until we show they're equal. So I might go over here and write sine squared of x and write Pythagorean identity. Because that's the identity that I used to equate 1 minus cos squared to sine squared. And then I can say left side equals right side. And we're done. Okay, we want to prove this identity and state the non-permissible values. You know what? Let's not state the non-permissible values. Okay. Finding the non-permissible values here will fit better into a different lesson. So I'm just interested in the proof. So how are we going to prove this? Well, look, we have to listen to the strategy here. You have to take the left side and turn it into the right side, or take the right side and turn it into the left side, or work on them each back and forth so they become each other. I hope you see that we're not going to do anything to the right side. Tan x is as simple as it gets, really. Why would we want to try to turn tan x into the stuff on the left? That doesn't even make sense. You want to work on something that's complicated and make it simpler. Well, sine of 2x is 2 sine x cos x. And I'm using a double angle identity. Now, I'm also going to use a double angle identity for cos of 2x. But I have 3 different choices for cosine of 2x. Right, so hopefully you're looking at your formula sheet here. I'm going to go to a different screen. We have cosine of 2x is equal to a number of different things. Cosine squared of x minus sine squared of x. Cosine of 2x is also equal to 2 cosine squared of x minus 1, and cosine of 2x is also equal to 1 minus 2 sine squared of x. And I'm pretty sure I have those, but in my seminar this morning I thought 2 times 5 was 15. So my brain is not yet warmed up. Those are correct? So now thank you. So you have to now say, which of those is my best move? Which of those will not result in me stepping in a bunch of mud and making things tough in my day? We're going to take cos of 2x and we're going to add 1 to it. So I think the answer might be obvious for many of you, but if you said, well, I'm going to try this, don't write this down, please. Well, this is not nice. It's messy. It's got 3 different terms. And by the way, if you did that, there's still a way to get out of the mud. But there's a way to avoid the mud. And it's not by putting 1 minus 2 sine squared of x in, because 1 plus 1 is 2. So we're still left with multiple terms. The way to totally avoid the puddle of mud is to put in 2 cos squared x minus 1, because then when you add 1 to that, the negative 1 in the 2 cos squared x minus 1 cancels with the positive 1, and you're left with 2 sine x cos x over 2 cos squared x, which you shouldn't need to write 2 cos squared x as cos x times 2. I'm just doing it that way to demonstrate to you that the cosines cancel on the top and the bottom, leaving you with a cosine of x on the bottom. The numbers 2 and 2 cancel on the top and the bottom, leaving you with sine x over cos x. And I know that you know sine x over cos x is tan x, but you're not done until you show that they are equal to each other, identical. So now we write tan of x, and you can say left side equals right side. But we need to put quotient identity. Because that's the identity we used to go from sine x over cos x to tan x. I know it seems like childish that we have to do this, but we have to. Any questions with the second proof? Again, if you go to your textbook, There's a similar question. This one's on page 311. Seeing no questions, let's move on to example 3. Prove that this is true for all permissible values of x, and what are the non-permissible values? Well, let's talk about the non-permissible values first. I'm going to rewrite this equation so that I can see where all of the divisions are, where all of the division occurs. There is division by this thing. Somewhere in this equation, we are dividing something by sine of x plus 1. And what that means is that sine of x plus 1 cannot equal to 0. That's going to lead us to actual non-permissible values of x. Somewhere in this equation, we are dividing by cosine of x. We're dividing that entire top by cosine of x, which means that cosine of x is not allowed to be 0. Now, if you ended your investigation there, you would get all the non-permissible values, but you wouldn't get full marks on a diploma exam or a written response, because we are also dividing by 0 here, not dividing by 0, we are also dividing by something in those other two places. And unless you identify that these are two places, this and this are two places where non-permissible values enter into the discussion, you will not get full marks. You can now say, well, yeah, but all three of these are the same problem, that cosine of x cannot be equal to 0. And then you have to solve these. An intermediate step here would be to write sine of x is not equal to 1, negative 1 rather. So where is sine of x negative 1? It's equal to negative 1 at the bottom of the unit circle. So our non-permissible values are that x is not equal to 3 pi over 2 plus multiples of 2 pi. Because if you're at the bottom of the unit circle at 3 pi over 2, any full rotation will take you back there. And then cosine of x is not equal to 0. This is interesting. Cosine of x is not equal to 0. Cosine of x equals 0 at the top and the bottom, so we would put pi over 2 plus multiples of pi. Pi over 2, negative pi over 2, pi over 2, 3 pi over 2, etc. But do you see that this statement includes the statement above it? So you could say, and you should say, that x is not equal to pi over 2 plus multiples of pi. It's interesting to note here, everybody, if you didn't pay attention to this, you would still get the right answer, but you wouldn't get full marks, because you didn't address the other places or the other reasons it could be 0. All right, now let's prove this beast. I don't think there's really much we can do with the left side. So let's work on the right side. Here is a case where writing everything in terms of sine and cosine is a step backwards, I think. Why don't you factor out secant of x? If we factor secant of x out, you don't have to. You could write everything in terms of sine and cosine, and I think we will. I want to show you what would happen if you did it that way. But I'm going to factor that secant of x out. And I haven't used an identity here. I'm going to use an identity now. And some of you will say, and I can get on board with it, that what I'm doing now, let me write it down first, that what I am doing now is no different than writing everything as sine and cosine. I've just factored it out first, and that's a fair assessment. I need to write reciprocal identity here, and I wouldn't abbreviate anything on a written response. And now I have a complex fraction. So I am going to multiply the top and the bottom of this fraction by cosine of x. The cosine x here and here cancel. So I'm left with 1 minus sine of x over cosine squared of x. Now, I'm just going to address this. I hope nobody thinks you could do this, but I want to point out why you couldn't do what I'm about to say. You do not multiply the cosine x by the 1 minus sine x. It's not a distributive kind of thing. And the reason is there's a multiplication in between this piece and this piece. When you multiply three things together, the example I always use is 2 times 3 times 4. You go 2 times 3 is 6, and then you multiply by 4. You don't go 2 times 3 and 2 times 4. That's if there's a plus in there. Okay. Now, I'm going to bring down this other one so that you can see it. I believe it's that. Now, it may say sine x plus 1. It does, but I'm going to write it this way. I don't know if any of you see this. How many of you see how these are going to become equal? What we're going to do is recognize that cos squared is 1 minus sine squared. Oops. Yeah, 1 minus sine squared. And also recognize that 1 minus sine squared is a difference of squares. It can be factored. So we end up with 1 minus sine x on the top. I guess we should put Pythagorean identity here. And on the bottom, 1 plus sine x, 1 minus sine x. That's a thing of beauty because the 1 minus sine x as a factor on the top and the bottom takes us to what we want to get, which is 1 on the top and 1 plus sine x on the bottom. By the way, if you had written this, I mean, they're the same. You don't need to rewrite it, I don't think. I don't think you need to rewrite this as 1 plus sine on the bottom. Final example. This looks like intimidating. We're not going to worry about any non-permissible values. We want to prove it. I mean, really, it looks intimidating. But with a bit of algebra, you'll see how it comes together quite quickly. I think this is obvious. Well, I have to be careful here. To me, it's obvious that this is not going to be as simple as working only on one side. We're going to have to work on one side. We're going to have to work on the other side and get them to be equal to each other. So one of the things I look at here is I have sine of 2x. Well, that can be written with a double angle identity. And where we go on the left side has nothing to do with trigonometry. It has to do with your factoring and canceling skills. There's a common factor of cosine of x on the top. So I can factor cosine of x out and be left with 2 sine of x minus 1. That's kind of interesting. I mean, I really hope everybody sees a connection between this, which is on the top of the expression, and this, which is on the bottom. 4 sine squared x minus 1 is a difference of squares, which when you factor, you get 2 sine x plus 1, 2 sine x minus 1. That's a good thing, right? Because these will cancel. And then I would say to you, I think we've gone as far as we can go with the left-hand side. I don't think there's anything really you can do with it. Let me ask you a question. How many of you see the right-hand side is equal? Let me rewrite this so you can see it. We're left with cosine of x over 2 sine x plus 1. How many of you see that that's exactly what we have on the right-hand side? No, eh? What can we do to the top?
Take a cosine out.
Good. We'll take a cosine of x out. And what do we have left? Our friend sine squared x plus cos squared x. Now, we don't need to justify what we just wrote because we didn't use an identity. This is over 2 sine x plus 1. And this becomes cos of x over 2 sine x plus 1 because of a Pythagorean identity. I believe here, everybody, I think it'd be a really good idea on a written response proof for you to do this. It's not like the old school way of doing things where you're always moving down and you're showing substitution. But you're saying you're going from here to here with a Pythagorean identity. I know if I were marking a diploma exam and I saw that a student wrote that I have in green up top, I would go, okay, they know what they're talking about here. They know that's one, so that's why they're not writing it. And now, the formality, of course, is to say left side equals right side and be done with it. I did say that what I would do is this one, by not factoring first, you would write this as 1 over cosine of x minus sine of x. Again, pay careful attention to where I wrote the sine of x. I could have written it. I could have written it here, and that's not wrong, but it's not visually as useful as writing it here. Times 1 over cosine of x. I like to describe this point I'm trying to make about the alignment as there being 3 different lines of text. There's numerators, there's denominators, and there's operations. Divided by, times, minus, all that stuff. And then over cos of x. We already did this. I'm not going to write it down, but you would if you were doing it this way, write reciprocal identity because you're using a reciprocal identity. Then you would multiply top and bottom by cos of x. And you would get cos squared of x on the bottom. Now, my conversation earlier, I think it's gone. Maybe it's not. Yeah, it's gone. About when I multiplied that cos x through, I only multiplied it by the one thing because they were being multiplied. Here, this is being subtracted. So I have to take this and multiply it by this term and multiply it by this term. When I multiply the cos by the 1 over the cos, I get 1. When I multiply the cos by the sine times 1 over cos, the cos is canceled, so I'm left with sine x. And I'm not going to finish this. We're back at a step that we saw when we did it by factoring first. Now you'd change the cos squared to 1 minus sine squared. Factor and cancel. So hopefully you've built up some good skills in terms of working with identities. This is the section on proving identities. Remember, it's practice. It's not all for homework. When you take a look at this problem set, I don't know what the 1 to 26 is. I don't know what that is. That's part of the next piece. When you look at the textbook sections, not all of them are proofs. If you have difficulty with factoring things to simplify them, then there's a question in there that says factor to simplify, but it's not a proof. If you want to work exclusively on proofs, there are questions in here that say prove, and that's what we're working on today. There are also tons of extra examples. Now, on page 26, there's an extra section on sum and difference identities that some of the problems were suggested. Some of them are proving things using sum and difference. So if you want specific proofs in those areas, page 26. On page 30, there's specific proofs involving double angle identities. The answers to the textbook are almost non-existent. I mean, they'll kind of show you the proof, but the solutions for the extra practice problems are really detailed. Okay. Got lots of practice that you can be working on. We're working on this today, tomorrow during the seminar, and tomorrow during class. Your exam is next Monday, which aligns with a seminar day. So it'll be starting the exam shortly into the seminar, and you have until the end of class. Get to work. I need to just do a couple quick things, and then I will be around to help you out.